chapter, we talked about the autocorrelation. So remember, a random process, x of t, is just a sequence of random variables. So at each time, x minus 2, from time minus infinity up to x minus 2, x minus 1, x 0, x1, x2, and so on and so forth. At each time like that, each of these elements of the random process is by itself a random variable. So what we want to know is how similar are how similar is this process at different times. So for instance, let's let that be time. Here's a process where nearby elements are very similar. So for instance, it doesn't move very much from time to time. Moves a little bit, but not very much. If you know the value of the process at a particular time, it's highly correlated with the next value. In other words, it tells you quite a bit. If you know the value of the process at this time, it tells you quite a bit about what's going on at the next time. On the other hand, here's a process where there's very little correlation from time to time. So this is highly correlated. If I know that the current value is this, then I expect very little deviation at the next time. Here it's highly uncorrelated. If I see this particular value at this time, the next, that basically tells me nothing about what's going on the next time. So we can use the same correlation measure, but when I apply it to two different times of a random process, we call it autocorrelation. We'll call it expected value, x of t1, x of t2. Like this. So this, because at each time the random process is a random variable, this expectation behaves in exactly the same way as the correlation measure. So for instance, let's actually back up a little bit and do a correlation example. So let's let x be equal to a Gaussian random variable with mean 0 and variance sigma squared. Actually, let's give a particular value to variance. Let's say that's 1. And let's let y be another Gaussian random variable, mean u equals 0, and the same variance. And let's say x and y are independent. Actually, for the purposes of this example, it doesn't even matter that they're Gaussian. So the correlation between these two random variables is, because they're independent, I can split it up into expected value of x, expected value of y, which is 0, 0. Okay, now let's form two different random variables, u and v. U is equal to, let's say, what I'm going to do with u and v is I'm going to mix parts of x and y. So they'll be a little bit correlated, but not completely correlated. They'll have some correlation, but not total correlation. So let's let u equal 0.64 times x plus 0.36 times y. Let's let v equal 0.36 times x plus 0.64 times y. Okay, firstly, let's show that these new random variables u and v have the same variance. Actually, let's calculate their mean and variance. So what's the expected value of u? It's the expected value of 0.64 x plus 0.36 y, which is equal to 0.64 times the expected value of x plus 0.36 times the expected value of y, which is what?
0.
Is 0. And similarly, I can argue that the expected value of v is 0. Okay, variance of u, because the mean of u is 0, variance of u is equal to the expected value of u squared, which is equal to, oh, I'm sorry, I screwed this up. These numbers don't work out properly. This should be 0.8x plus 0.6y, 0.6x plus 0.8y. I jumped ahead to the end there. But it doesn't make any difference here. You might be wondering why I'm being obsessive about 0.8 and 0.6 there instead of just charging ahead with the numbers I had. It's because they work out to variance exactly equal 1, as we're about to see. So, expected value of u squared is the expected value of 0.8x plus 0.6y squared, which is the expected value, okay, 0.8 squared is 0.64 x squared plus 0.6 squared is 0.36 y squared plus 2 times 0.6 times 0.8, which is 0.48 xy. If I distribute the expectation, what's the expected value of x squared? Can you get it from up here somewhere? 1. It's 1, because the variance of x is 1 and its mean is 0. So the expected value of x squared must be 1. So that's 0.64 plus, what's the expected value of y squared?
1.
So 1. What's the expected value of x times y? 0. So they're independent, and each of their expectations is 0. So that's plus 0, and then all equals 1. Okay, you can go through the same procedure with v, but it should be clear by the symmetry that that variance is also equal to 1. So bar u